Hey everyone, I'm James. Welcome to another episode of Follow Suits. In my last episode, I looked at how an eclipse shadow forms, and I was able to create that on an actual scale physical model. In this video, I'm going to examine the movement of an eclipse and why it moves from west to east, despite us seeing the moon rise in the east and set in the west. And then I will again demonstrate that on a scale physical model. As I mentioned before, I witnessed the 2017 eclipse over the United States from the summit of Mount Bora, Idaho, with an elevation of 12,662 feet. From that height, we could clearly see the shadow approaching from the west, with the soft leading edge of the umbra racing across the landscape toward us. Then totality hit and put on one of the most awe-inspiring sights I've ever seen. When it was over, the shadow slid off towards the east as it made its way to Wyoming and points east. I saw all of this with my own two eyes. I've seen that west to east movement of the eclipse shadow, despite the moon rising in the east and setting in the west. I know from first-hand observation this is how it works, but a lot of people would beg to differ with me. Remember that video I linked to in my previous episode of people, including a NASA scientist, trying to explain how an eclipse works? Well, along with the usual comments of liars, NASA fails on YouTube, this is serious fraud, and the old classic, NASA is fake. There was a lot of people who thought something was fishy with their explanation of the west to east movement, and I'll admit, they didn't do a very good job explaining it. BS. If the moon is traveling fast enough to cast a shadow west to east, then every night the lit moon would travel the same direction. A shadow from an object backlit from a fixed sun cannot go the opposite direction of the object casting the shadow, unless of course there's some sort of lensing or other object which has never been truly explained. No, we've explained everything. And when the video suggested that the moon orbits twice as fast as the Earth rotates? What? The moon rises in the east and sets in the west. Something isn't right here. Correct me if I'm wrong, but it takes 24 hours for one Earth rotation, and it takes 1 month for the moon to complete a full orbit, which is why we have different moon phases every 29 days. So how does the moon orbit faster? The Earth spins 27 times faster than the moon. The moon's shadow should move east to west. Distance traveled, or speed, has no bearing on this. Actually, distance traveled and speed have everything to do with this, and I'll get to that. But finally, NASA's explanation is complete BS. They can't reproduce this on scale heliocentric models. As a former NASA employee, challenge accepted. And that was just one video. There's a lot of people who are too quick to dismiss something simply because they don't understand it. There's a lot of things in motion with these eclipses, and they can be kind of tricky to wrap your head around and explain. But hopefully by the end of this, it'll all make sense. I'll be using my out-of-scale diagrams to illustrate the basic concepts, and then my 2-scale physical model to create 2 actual west to east eclipses. There's a lot here to unpack, so I'm going to build the explanation up a little bit at a time. I'll be talking a lot about angular velocity, or degrees per hour, and linear velocity, or kilometers per hour. Each is important at different stages of the explanation for different reasons. And before I get started, please keep in mind that these diagrams are not to scale. Not to scale. As I demonstrated in the previous video, I have to exaggerate the various components in order for them to be big enough and close enough to each other to actually see. So, let's start with a few relevant facts and figures. When viewed from above the North Pole, the Earth rotates around its axis in a counterclockwise direction. Its angular velocity is 15 degrees per hour, and a point on the equator rotates at a linear velocity of 1,670 kilometers per hour, taking 24 hours to complete one rotation. A point on the equator will travel just over 40,000 kilometers around the circumference of the Earth in 24 hours. Now let's put the moon in there. The moon revolves around the Earth in the same counterclockwise direction. This is a fact that a lot of those commenters don't seem to realize. They're going in the same direction. Its angular velocity around the Earth is about 0.55 degrees per hour, and its linear velocity around the Earth is just over 3,600 kilometers per hour. The Moon completes its almost 2.5 million kilometer orbital path once every 27 days, or almost 656 hours. So that means the Moon travels at a much slower angular velocity than the Earth, but more than double the linear velocity of a point on the equator. So yes, the Moon travels twice as fast in its orbit as a point on the equator moves, but because it's so far away from the Earth, it also has to travel 60 times the distance just to make one round trip. So if the Moon is revolving in one direction, why does it look like it's moving in the exact opposite direction? Well, that's where the difference in angular velocity comes in. As the Earth rotates, the Moon will come into view as an observer looks east. And then after a while, the Moon goes out of view to the west as the Earth rotates away from it. But because the Moon is moving in the same direction around us, it won't be in the same spot the next night. In 24 hours, it will have moved just over 13 degrees along its orbital path to the east. So instead of getting a moonrise every 360 degrees, that observer on the Earth will have to rotate over 370 degrees to catch up to where the Moon is, with the moonrise and set getting a little later than the day before. The same thing the next day and every day after that. This cycle repeats roughly every 27 days. This is why the Moon's actual motion is from west to east, but the Earth's greater angular velocity in the same direction makes the Moon's apparent motion go from east to west. In fact, if the Earth were to suddenly stop rotating, the Moon in the sky would reverse direction and start going from west to east. So let's apply all this to an eclipse, where the interplay of angular and linear velocities will become apparent. Let's start with our eclipse's umbra and observer in these positions, with the umbra west of our observer. Our observer has to look in an easterly direction to see the Moon. Because of the Moon's greater linear velocity, the eclipse will catch up to and overtake the observer on the Earth. Let's look at that again, and this time pay attention to the direction that the observer has to look in order to see where the Moon is. By the end of it, they are looking in a westerly direction to see the Moon. This is because of the Earth's greater angular velocity. The Moon and its eclipse actually moved from west to east, and the Moon's apparent motion in the sky to an observer on the surface went from east to west. One more time. So hopefully that all made sense. You can see why it's kind of a tricky concept to explain. So enough of the diagrams. It's time to create some real-life, to-scale, west-to-east eclipses. My scale Sun, Moon, and Earth system should be getting familiar by now. Scale sizes, scale distances, you know the drill. In my previous video, I used them to demonstrate the umbra-penumbra structure of an eclipse shadow. So this time I'm going to add movement and create two different eclipses to demonstrate that movement. On the first one, I'll be aiming the eclipse at the North Atlantic, starting from the US East Coast, since it'll show up on the blue of the ocean better. But I'll be using the same basic parameters as the 2017 eclipse. So it'll be roughly in August, mid-northern latitudes. It'll be about an hour and a half in length, which was the coast-to-coast time for the eclipse. And on the back of the globe, I've put these time markers. In 90 minutes, the Earth rotates about 22 degrees. I've broken that down into increments of 10 minutes. A point on the equator will rotate about 6 centimeters. So for my Moon, I've marked the distance that it's going to travel up here on the cross pipe. The increments are also in time traveled in tens of minutes. So this will be the distance the Moon travels over 90 minutes and covers 9 centimeters. So that's a little shorter than it should be. While my scaled down Sun was perfect in the last video for the static eclipse, when I add movement, it'll introduce a bit of an angle that wouldn't be there in real life. So I've compensated by doing a shorter distance traveled for the moon. So it'll go 1.5 times farther than a point on the equator instead of twice as far, but it's still going to go in the same direction by a greater amount and have the same effect on the globe. So I'll take a picture of the eclipse with the Earth and the moon both at their 0 mark, and then I'll move each of them to their next time increment until I get all the way to the 90-minute mark. And then I'll put them all together for a short animation of the eclipse. So let's take a look. And so you can see that penumbra a little better. Here's the same animation in that difference mode that I used in the last video. So on the second eclipse, I'll be looking down on it from above the North Pole so that we can see the angles that an observer on the surface would be observing the moon at. And I wanted to show an observative experience over the course of a short day. So they're going to be in Acadia National Park in Maine during the winter solstice, which is only going to get about 9 hours of sunlight. And in that time, the Earth is going to rotate about 135 degrees, and our observer in Acadia will travel just over 10,000 kilometers. And meanwhile, the eclipse, along with the moon in its orbit, will travel more than 3 times as far at 33,000 kilometers from here all the way to over here. And it'll be basically starting and finishing in open space. And I've added these whiteboards so that we can actually see it moving as it travels across the plane that bisects the globe. So let's take a look. In relation to the day side of the globe, this eclipse will start far to the west in open space, and I'll track its movement over 9 hours until it gets to the other side. Meanwhile, I'll mark our observer in Acadia with a green X and draw a red line in the direction they would have to look to see the moon. Our observer starts by looking east to see the moon at dawn. After a day of the moon traveling east, the observer now has to look west to see the moon. One more time. So there it is, an eclipse on a real physical model using the speeds and directions that we're told and getting that west to east movement of the shadow and still getting that east to west apparent motion of the moon to an observer on the surface. Not only does it all work, but it works so well that we can predict eclipses for centuries to come. I started planning my 2017 eclipse journey 8 years prior to the event, and it occurred exactly when they said it was going to occur. So that about wraps up eclipses for now. Hopefully these 2 videos helped you understand how and why eclipses function the way they do. And I didn't even get to why they only happen once every 1.5 years or so. Maybe that'll be another video down the line. And at some point I'd like to get to lunar eclipses. And if you happen to live in North America, start making plans now for our next big eclipse, which is happening on April 8th, 2024. It promises to be even better than the last one. So get in the path of totality if you can, because that really is the only way to truly experience an eclipse. It's amazing. So if you like this video, hit the like and subscribe, and thanks for watching.